Right, good day, girls. We are carrying on with the sports theme, so we have a swimming costume with a hat today. Fine swimming costume it is. So, we're going to be doing in paper 1 now, complex numbers. So this is part of paper 1, algebra and calculus. You'll be working in this textbook now, okay, starting from page 1. They have an alternate way of representing the number system on page 1 of the textbook, so have a look at that as well. I'm going to do it slightly differently, and you need to be very comfortable with the numbers that number system and it's something you need to know up to the end of matric. We don't explicitly teach it to you again, but you do need to know it. So the number systems. Well, when man started to count, we were walking around in our little, there's virtually nothing on back in the day. Okay. The first things you did was start to pick up objects. And if you're picking up objects, okay, the first number of rocks you can have is 1, then 2 rocks, and then 3 rocks. So those, okay, your first numbers are the set of n for natural numbers. So I represent the number system, which I'm sure you've seen before in grade 9, like those Russian dolls. Okay, so where you get dolls within dolls, sets within sets. So our first set of numbers that we start off with is a set of natural numbers, and remember the set of natural numbers is an infinite set. Okay, so we could start with 1, and we could have 52, whatever, 7, 2, just random examples, 3. So we had the natural numbers. Then it took several thousand of years to come up with another number, and if I'm correct, it came up in India, and that is a set of natural numbers plus naught, okay, which we call the whole numbers, or the counting numbers, 0, 1, 2, 3. So that is your set of whole numbers. So to include the whole numbers in the set, here's your set of whole numbers, and the only number we've added is 0. So the number 723 is a natural number and it's a whole number. Okay, a number can belong to more than one set at once, just like you guys belong to this class, the AP class. Okay, so here's your class. You also though belong to the grade. You're in both of those sets. Okay, and then there was a problem, because if you're working in the natural numbers or the whole numbers, and we know that there's an operation of subtract, and you go 7 take away 11, well, there's no number that deals with that. So we made up the negative numbers. Negative numbers are created. Okay, I can't show you -4 apples. Okay, so the next set of numbers we had will include the negative numbers, and we have the set of integers, and the symbol for the set of integers is Z with an extra number, with an extra line. So that's your integers, and goes down, -2, -1, 0, 1, 2, goes down to negative infinity and up to positive infinity. If I said to you, are there more numbers in the set of natural numbers or in the set of integers? Good, the answer is the same. Okay, because they are both infinite sets. You can't, an infinite set is an idea, it's not a number of things. So the set of natural numbers is as big as the set of integers. Right? So now we can include the set of integers around that. So there's the set of integers, and now we can add negative natural numbers. So -2, -1, 2, 3, 4, whatever. Okay, all your negative natural numbers, okay, belong to the set of integers, right? Okay, then we have a problem with division, okay, in that if you go 1 divided by 2, it's not in any of these sets. Okay, so there's a new set of numbers. The problem is we can't really list those set of numbers. We can just define those sets of numbers. Okay, and that set of numbers is defined as this Q with an extra line, which is a set of rational numbers. Okay, and the definition for the set of rational numbers, we can't list them, because what do you write if you're going upwards what's the first rational number after 0? Well, you might say 0, 1,000 zeros 1, and you can put a billion zeros there. We cannot tell you what the next rational number is after 0. So we can't list them like this. So all we can do is give a definition, and the definition of the rational numbers is any number that can be written in the form a over b, okay, where a and b are elements of, that's the symbol elements, are elements of the set of integers. Okay, I will take photos of these and send them to you after your lesson for anything you can't read. AB is an element of the integers, and b cannot be equal to 0. So that is your strict definition of your set of rational numbers. I think it's worth knowing. It's any number that can be written as one number over the other number, where the top number, the numerator and the denominator are both integers, okay, and the denominator cannot be equal to 0, which is obvious because that's undefined. Right, get that down, please. We're not finished with the circle, by the way, but I'm going to rub out the top bits. Okay, so we had the natural numbers, then the whole numbers, then the integers. Okay, so the number, for instance, 52, okay, is a natural number, but it also belongs to the set of whole numbers, and it belongs to the set of integers. And 52 would also, any natural number, okay, is also a rational number, because it meets the definition of being able to be written as a fraction. 52 is 52 over 1. So the natural number, the number 52 is a natural number, a whole number, an integer, and it belongs to the set of rational numbers, just like you could be in your class, in your grade, in the school, in the province. Okay, you can belong to more than one set at once. So also what's included in the set of rational numbers, which might not be so obvious, is any recurring decimal. For example, negative 0.3 recurring, because any recurring decimal can be written as a fraction. So that, for example, is negative 1 over 3. So it meets the definition of what a rational number is. And likewise, any terminating decimal, any decimal that comes to an end, for example, negative 1,3572 could be written as negative 13,572 over 10,000. Okay, so those also belong to the set of rational numbers. Then we get numbers which are irrational. Okay, and the symbol for irrational is, it's a separate set. A number can't be a rational and an irrational number at the same time. Okay, so you've got the irrational numbers, and in maths, the symbol for not something, so it's rational, symbol for rational, and then not is that extra line, just like complementary sets. Okay, this over here we'd read as the complement of A. Okay, in other words, it's not, okay, a rational number. So the definition of an irrational number is simply a number that cannot be written in the form A over B, where A and B are integers. Right, go write down what type of numbers are irrational numbers. Give me a few examples. Okay, so I asked you for some examples of what irrational numbers are. Okay, example of an irrational number is any non-terminating, non-recurring decimal. So a decimal that doesn't come to an end and doesn't repeat. So non-terminating, non-recurring decimals can't be written as something over something, an integer over an integer. Any non-perfect surd, in other words, the square root of 10, the cube root of 20, anything when you find a root, okay, and it doesn't give you a natural number, is going to be irrational. Okay, the number pi, which is the ratio of the circumference of a circle over diameter, okay, we can prove that that's a number that never comes to the end. Likewise, Euler's number, okay, with the symbol for that is E, which you'll deal with in matric, also is an irrational number. So we've got the irrational numbers like root 5 and pi, which is a completely separate set. Okay, so you can't be in the irrationals and in the set of rationals at the same time. Now together, okay, the irrational and the rational numbers, okay, make up, in the square box over here, these numbers combined are the real numbers. Okay, so your definition of the real numbers is, well, a way you can represent the real numbers is the rational numbers plus the irrational numbers make up the set of real numbers. So if your sample space is the real numbers, so here's all the real numbers in that square, they'll either belong to the set of rational or they'll belong to the set of irrational numbers. Together, that whole sample space will be the set of real numbers. Okay. Right, so the real numbers met all our mathematical needs because they're closed under addition. So in other words, if you add two real numbers together, you'll get a real number. If you subtract two real numbers together, you'll still get a real. If you multiply two real numbers together, you'll get a real. And if you divide, with the exception of dividing by 0, which is undefined, if you divide two real numbers together, you'll get a real number. However, then there was a problem, because finding the square root of a negative number. Well, the square root of 16, why is it equal to 4? Because what the definition of a square root means, what times by itself will give you 16. Well, 4 times by itself is 16. So 4 times 4 is 16, so the square root of 16 is 4. The problem is, what about the square root of a negative number? And the problem we have is the square root of negative 1. What two real numbers times together will give you negative 1? Well, no real numbers times together will negative 1. So we start to invent and make up a new number. And that's perfectly legal to make up a new number, just like we had the problem with subtraction. 5 minus 9 didn't exist in the real number system, so we made up negative numbers. Now we're going to make up a number, okay, to deal with that. Okay, so we've got the problem of what is the square root of negative 1. Okay, and to deal with that problem, there's nothing in the real number system that if you times it by itself, you're going to end up with, in fact, with an answer of negative 1. Okay, so we make up a number, okay, and that number is called I. Okay, so the square root of negative 1 we call I, okay, which is an imaginary number. Now, just like the square root of 16 is 4, implies that 4 times 4 must be equal to 16. So, if the square root of negative 1 is I, then I times I must be equal to negative 1. Just like the square root of 16 is 4, then 4 times 4 is equal to 16. Okay, and likewise, if the square root of 16 is 4, 4 squared must be equal to 16. So likewise, if the square root of negative 1 is I squared is equal to negative 1. And that's really important, both of these things that you have. Okay, the square root of negative 1 is defined as I, the imaginary number, and I squared is equal to negative 1. Okay, so get that down. So an imaginary number now, okay, is any single term with I in it. Remember, where I is equal to the square root of negative 1. So an imaginary number is any single term with I in it. Okay, so for example, the term I is an imaginary number, 3i is an imaginary number, negative 17i is an imaginary number, and 2 over 3i is also an imaginary number. So a single term can't be a real number, and a single term can't be a real number and an imaginary number. So we've got here, this whole thing over here, the rationals and the irrational, and the irrationals and the rationals combined, remember, makes up the set of real numbers. Separate from that is another set of numbers called now the imaginary numbers. For example, negative 2 over 3i, 17i, and I. Okay, I should really have a circle, that will confuse you. Okay, so we've got the reals. Separate to that, we actually don't even use a circle here. We're going to have the imaginary numbers, I, m, okay, which could be 2i, for example, negative 3 over 2i, just I. Okay, so you've got the reals in that bit, the imaginary bit in that, and together, if you have a real part, a real term combined with an imaginary term, okay, it makes up what we call the set of complex numbers. So just to go through it, if we took the number 52 again, and I said to you, what sets of numbers does that belong to? Okay, it's a natural number, okay, it's a whole number, it's an integer, it's a rational number, it's a real number, it's not irrational, it's a real number, okay, and it also belongs to the set of complex numbers. Okay, so anything which is a real number is also a complex number, anything with an imaginary number is also a complex number. In other words, okay, if you had, that should be, let me just write that over here, any single term with I in it. Okay, the imaginary number is any single term with I in it. So if I had to draw the set of complex numbers. Here's the set of complex numbers. Okay, the symbol for complex is C with an extra line. Okay, the complex numbers, okay, consist of two parts. On the one side we have the real parts, and then we have the non-real parts, okay, or the imaginary parts, and the real and the imaginary parts together make up the set of complex numbers. I'll give you a definition of complex numbers now. Right, so some examples of complex numbers. Remember, the symbol for complex numbers is C with that extra line over there. Okay, complex numbers consist of the real numbers combined with the non-imaginary numbers. Okay, sorry, real numbers and imaginary numbers. So an example of a complex number would be 2 plus 3i. That's a single complex number, and that complex number consists of a real part, and the real part in that particular example is 2, and an imaginary part which is 3i. Okay. Another example of a complex number would be just the number negative 17 over 2. Okay, it is a complex number. I mean, it's a real number as well, but it can be considered a complex number where the imaginary part is 0. Likewise, 5i, which is a non-real number, it's an imaginary number. Okay, 5i is a complex number where the real part is equal to 0. Right, some key ideas before we carry on, and Nandipa will be doing this board with us. So Nandipa, if you've got a to the m times a to the n is multiplying two powers of the same base, what do you do to the exponents? That's correct, you add them. So a to the m times a to the n is a to the m plus n. So if you have the imaginary number, whenever we work with an I now, it's not like a normal variable, it's the imaginary number. It's, in other words, I squared is negative 1, but all I want you to, the properties of multiplying powers of the same base still holds true. So I squared times I to the 7, add the exponents, 2 plus 7 will be I to the 9. Likewise, if you've got a to the m all to the power of n, that'll be a to the m times n, in other words, a to the m n. So Nandipa, I to the 5 to the power of 4 will be what? Fantastic, I to the 20. The other key idea is that if you've got negative 1 in brackets to an even power, it'll be equal to 1. For example, negative 1 squared would be 1, negative 1 to the 50 would be equal to positive 1, and likewise, negative 1 to an odd number would be equal to negative 1. So example, negative 1 to the 5 would be negative 1, negative 1 to the 2003 would be negative 1. That's odd. That is equal to negative 1. High five yourself, Nandipa. Right, now we're going to start working with imaginary numbers, and Megan's going to be helping us here. And so you're evaluating I to any power. And your key idea, remember, is that the square root of negative 1 is equal to I, but in this case, more importantly, I squared, the imaginary number squared, is equal to negative 1. So if you in the examples you asked to evaluate I to the 5, if it's an odd number, okay, I would always first of all rewrite it as an even power. An even power times I. So how can I rewrite I to the 5 as I to the something with an even power? Good, Megan, it will be I to the 4 times I, okay, because I means I to the 1, so I to the 4 times I to the 1 is I to the 5. Now, once you've got it to an even power, then you're always going to get it as I squared to something. So how can I rewrite I to the 4? I to the 4, I'm going to write as I squared all squared. Okay? So I squared all squared, okay, is going to be I to the 4. When you raise a power to another power, that's why I went over that, you multiply the exponents. So you've got I squared times I. Okay? But what is I squared? I squared is equal to negative 1. So you end up with negative 1 squared, because I squared is equal to negative 1. So you get negative 1 squared times I. and negative 1 squared is just 1, so you get 1 times I. So your answer is I. For all of these questions, your answer is always going to be 1, or I, or negative I, or negative 1. So here, my answer is I. So there is example 1. Well done, Megan. Okay, so now, okay, in this one, okay, over here, if it was an odd power, we had to rewrite it as an even power. So if it was odd, you had to rewrite it as an even power times I. Okay, but if it's even, okay, you're just going to write it as I squared. So if it's an even power, you're going to write it as I squared to whatever. Okay, you don't have to go through this extra step. Okay, so I to the 10, how can you write that? Well, we can write it, good, Megan, as I squared to the 5. Okay, but what is I squared? I squared is equal to negative 1. So it's negative 1 to the power of 5. And negative 1 to an odd number, we discussed that just now, is simply equal to negative 1. Okay. Right. Get that down. Right. Lulu, you're going to be doing the next one with us. And we asked to evaluate I to the 87. So it's an odd power. So if it's an odd power, you always want to write it as I to an even power times I. So we want to have I to the something times I, right? So Lulu, what's going to go there? Indeed, it is going to be I to the 86. So this is I to the 86 times I. Okay, and now once you've got it to the even power, okay, you're going to write it as I squared to the something. So Lulu, what's going to go there? 2 times what is 86? 2 times, fantastic Lulu, 2 to the 43 is 86 times by I. Okay, now what is I squared? I squared is negative 1. So you're going to have negative 1 to the 43 times I. And Lulu, negative 1 to an odd number is, good, it's just negative 1. So you've got negative 1 times I, which is simply negative I. Okay. You can multiply 2 times I is 2I, etc. Okay. You can multiply a real number by that, by a complex, by an imaginary number, but you can't add because they're classified as unlike terms. Right. Okay, Lulu, you're on a roll, or are you exhausted? Oh, she says she's absolutely exhausted. So we are going to have who? Let's have Zonke. Zonke. Right, what are we going to do here? I to the 3001. Well, yes, it's an odd number, so what I have to do, I have to write it as something times I. Okay, and what's that going to be? I to the what? Okay, well, I to the 3000 times I to the 1. If you add the exponents, it's going to be I to the 3001. So you're going to have I to the 3000. Now, what I do with this I to the 3000? Well, I've got to write it as I squared, okay, all raised to the power of what? So 2 times what will give you 3000? Indeed, Zonke, it is 2 times 1500. Okay, will give us 3000. And I squared is what? I squared is negative 1. So I get negative 1 to the 1500 times I. And now you've got negative 1 to an even number. And negative 1 to an even number is just 1. So I get 1 times I, which is equal to I. Okay? After this lesson, you can take the rest of the day off because you did such an absolutely sterling job. Right. So the next thing I want to do, we'll get back to complex numbers, but you've got to be able to expressing surds in the simplest surd form, we call it. And you've got to be able to do it without a calculator. All of the question examples I'm going to do with you, you could do just straight with a calculator, but when you write NVTs in matric, you're going to have to be able to work those out without a calculator. At first year varsity and a lot of courses, you're going to have to be able to do it without a calculator. And once we get back to school, I'll give you a test where you're not going to be allowed a calculator either. So, your key ideas in this section is that if you've got the square root of a times b, you can do them separately. So it'll be the square root of a times the square root of b. For example, square root of 9 times root 16. You could go work that out. Okay, square root of 9 times 16 would be equal to, you could do that by going, well, the square root of 9 is 3 and the square root of 16 is 4, which is going to be equal to 12. You could do them separately. Okay, so you could go square root of 9 times square root of 16, which is 3 times 4, which is 12, or you could have times them together and you get 144, and then the square root of that is 12. Okay, so, but it's not implicit, because remember, if you think about adding under a third, the square root of a plus b is not equal to the square root of a plus the square root of b. For example, the square root of 9 plus 16, okay, what is that answer? It's the square root of 25, which is 5, but if you do them separately, you get 3 plus 4, which is 7. So you should be comfortable with that. The other thing you need to know in your sleep is the first 10 perfect squares: 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Right, in Calypso, you're going to be doing this with us. Okay, expressing surds in simplest surd form. So the question would be, that would the way we'd ask the question is, we'd say express root 50 in the simplest surd form. And if you go to your calculator in Seleco and press square root of 50, you can do that quickly. You'll check that you get an answer which is going to be the correct answer. But if you ask to do it without a calculator, well, what do you have to do? Well, the key idea is you have to rewrite this as whatever that number is. If it can be simplified into simplest surd form, you'd be able to have to write it as a perfect square times another number. Okay, so 50. Is there a perfect square that goes into 50? 1, 4, 9, 1 doesn't, 4 doesn't, 9 doesn't, 16, or 1's trivial. 16, 25 works. Okay, so how could I rewrite root 50? I could rewrite it as 25 times 2. And our law for surds says I could rewrite this as separate surds. With practice, you can skip out the step over here that I'm doing now. But you would have to show that step over there. That must be shown. I'd forgive you if you didn't write the next step. Okay, and then root 25 times 2, well, the square root of 25 is 5, and that is root 2. So you end up with 5 root 2. So root 50 is not in simplest surd form. In simplest surd form, it is 5 root 2. So if you go on your calculator and go root 50, it'll give you 5 root 2, but I want you to be able to do that without a calculator. Right, so let's do the next one, root 80. Well, if I think of my numbers, well, there's two ways we could look at this sum actually. So say you go through this perfect squares and you go, right, 4 works. It's not wrong to do that. So you could go, I'll show you another way now which is quicker. So you could go, right, that's 80, I could write that as 4 times 20. I can do those as separate surds, so I could write it as root 4 times root 20. Okay, and root 4 times root 20, okay, I could write as 2 root 20. But now, you've got to just check, is there a perfect square that goes into root 20? Okay, well there is, 4 goes into that. So I could write it as 2, 4 times 5, which is 2 root 4, 2 times root 4 times root 5, and 2 times root 4 is 2 times 2 times root 5, which gives me 4 root 5. Okay, I want you to go try to do root 80 in a quicker way than that. Right, so Karina, you're going to do this with us. Well, what would be a quicker way to do this? Well, the quicker way to do this, well, 4 went in there, but there's another perfect square that goes into root 80. What's the perfect square that goes, the bigger perfect square? 9 doesn't, but 16 does. So you can have root 16 times 5, okay, which is going to be, you can learn to skip out this step now. What's the square root of 16? It's 4, but you must show me that step. So you're left with 4 times root 5, which is the same answer as we got doing the other way. Okay, so well done, Karina. That was easy peasy, lemon squeezy. So root 63. Okay, what's the perfect squares? Well, 4 doesn't work. Okay, 9 does work though. So you can write it as 9 times 7, and then square root of 9 is 3. So you're left with 3 root 7. Karina, you are a legend. Well done. Right, Kiara. Okay, so your next heading is Rewrite the following non-real numbers in simplest third form. No calculator, show working. So you've got the square root of a negative number, okay, which in core you just write the answer. If you got that, you just say the answer is non-real. That's all you'd write, okay, and you'll stick to that. You're never going to use imaginary numbers in core maths. But in AP Maths, where we're working in the complex number system and we can deal with imaginary numbers, we can simplify this. Okay. So again, we use a concept that I could write this as square root of 98 times negative 1. Okay. Square root of 98 times negative 1. Now we can split it up as root 98 times the square root of negative 1. Now we've got to say, what's the square root? What's how can I rewrite 98 as something times something where one of the numbers is a perfect square? So if you go and run through them, 4 doesn't work, 9 doesn't work, 16 doesn't work, 25 won't go into 98, but 49 will. So you're going to have 49 times 2 is 98. And what's the square root of negative 1? The square root of negative 1 is I. So that's one term. Root 49 times 2 times I. Right? I isn't under the third. And then the square root of 49 is 7. The square root of 2 is just root 2. So you're left with 7 root 2 I. Okay. Right, so Kiara, try to do the next one. Square root of negative 48. So you can write that as soon as you get a negative, you can write it as root 48 times negative 1. In other words, we've got square root, Kiara, of 48 times the square root of negative 1. And how can I write root 48 in simplest third form? Well, is there a perfect square that goes into it? Well, 4 does. But if we carry on, 9 doesn't, but 16 does. So it's always better to pick the bigger one, otherwise you're going to have to do extra steps. So it's root 16 times 3. Okay, and the square root of negative 1 is I. And then the square root of 16 is 4. 3 we're going to leave as root 3. So you're left with 4 root 3 I. Okay, high five yourself, Kiara. Right, hello Jamana. You're going to quickly do these with us. So you've got adding, subtracting, and multiplying complex numbers, and basically it works like grade 1 algebra. Imaginary numbers and real numbers act as unlike terms, so you can only add an imaginary part to an imaginary part and a real part to a real part, just like you did in grade 1 algebra. So Jamana, 3i minus 4i will be negative I, and 2 plus 17 will be 19. So you're going to get negative I plus 19, then those are unlike terms, so you can't do anything more with it. So do this one for me, please. Okay, and if you're on negative 7i and you go 15 up, you'll end up at what? Yes, at 8i, and minus 4 minus 11 more is minus 15. So you have, in that complex number, you've got an imaginary part of 8i and a real part of negative 15. And with multiplication, same as always. Minus 4 times 2 will be negative 8, and I times I will be I squared. We'll worry about how we simplify those further now. Oh my goodness. Oh dear. Well, we had a mishap. I didn't stop recording. Sorry for the waste of time. Okay. Right. If I look at this quickly, if I've got 6i, if the question is evaluate 6i squared times 4i cubed, well, at least you got to see what goes on behind the scenes. 6i squared times 4i cubed, okay, is, okay, and remember, I can't believe I did that, I squared is equal to -1, okay, so Ariana, if we multiply this out, you're going to get 24, add the exponents I to the 5, but you've got to evaluate it all the way now, and 24i to the 5, it's an odd power, so I'm going to write it as 24i to the something times I, okay, so it's going to become 24, or I to the what times I is I to the 5, it's going to be 24i to the 4 times I, 24i to the 4 times I, okay, and I to the 4 is going to be 24, we can write I to the 4 as I squared, remember it's always going to be I squared all squared, times by I, and I squared is -1, so it'll be 24 -1 squared times I, and -1 squared is 1, so I end up with 24 times 1, which is 24i is going to be your answer. Okay, right. In the next one, Erin, let's do this one over here. Okay, you're going to times that out. So, if you're multiplying powers, don't forget you're going to add the exponents. So you've got I squared times I to the 4. 2 plus 4 is 6. So you're going to get I to the 6 plus 3 times I squared is 3I squared. Okay, minus I to the 33. Okay, plus 4I. Now you've got to simplify I to the 6 and I to the 33 and I squared. So I to the 6, Erin, is already an even power, so you can write it as I squared or cubed. 3I squared, or I squared is -1, so 3 times -1. I to the 33 is odd, so you're going to go right minus, and it's got to be I to the something times I, and it's an odd power, so I to the what? It'll just be I to the 32 times by I, and then we've got plus 4I, which we can't do anything with. Then over here we've got I squared. I squared is -1, so I get -1 cubed minus 3. Okay, I to the 32, you can start skipping out steps if you're comfortable with it. I to the 32, we've got to write it as I squared to the something. Will it be I squared to the 16 times by I? 2 times 16 is 32 plus 4I. -1 cubed is -1 minus 3. Okay, minus I squared is -1, so I've got -1 to the 16. Okay, so that's -1 to the 16 times I. Erin, you're doing so well, I'm so proud. Plus 4I. So I end up, I've made any mistakes, with -4. -1 to the 16 is +1. -4 minus 1. Okay, I'm an idiot. It's -4. -1 to the 16 is 1 times I is I. So I get -4 minus I. Okay, plus 4I, which gives us a final answer of -4 plus 3I. Sure, nice one. So let me just check that. -1 minus 3 is -4. I squared is -1. -1 to the 16 is 1. 1 times I is I, but there's a negative, so it's -I plus 1. I think that's right. Okay, and your last thing you have to do is exercise 1 in your calculus and algebra textbooks. Okay, page 3, and the whole exercise, I will send you the memo. Okay. Right, girls, thanks very much. Sorry for the behind the scenes look at things. Arrivederci.